Hello, my name is Kwan-seok Oh. I'm an integrated course student of Artificial Intelligence KU. My advisor is Professor Hung-il Seok. Today I'm gonna introduce about Learn, Explain, Reinforce framework that not only generate a map that can interpret the decision making of the model for diagnosing brain disease, but also use this map to improve the performance of the model. Alzheimer's disease is one of the most common degenerative disease, and it is one of the major causes of dementia. It accounts for roughly 60 to 80%, and there is the big limitation in that there's no clear treatment for Alzheimer's disease until now. Therefore, early detection of symptoms is important as it can slow the onset rate or improve cognitive function through drug treatment and rehabilitation. For this purpose, as shown in the figure on the right, brain disease is diagnosed through structural MRI, that is fMRI. Also, Alzheimer's disease is a disease that shows a continuous spectrum and can be divided into cognitively normal, mild cognitive impairment, and Alzheimer's disease from left to right. Therefore, various studies through deep learning have been conducted recently for the diagnosis of Alzheimer's disease. Even though these deep learning models achieve a high performance in respect to the diagnosis, there is a trade-off problem that cannot bring model interpretability due to the black box problem of deep learning. For example, the model has determined that the input is a brain with Alzheimer's disease, but it is difficult to provide an explanation for why it made this decision. Many XAI studies have been conducted to solve the trade-off between accuracy and model interpretability, which is a chronic problem in deep learning. Among them, attribution-based approaches such as layer-wise relevance propagation and class activation method have been famously used as methods for model interpretation. But they have a limitation in that they are difficult to interpret intuitively. Specifically, it was difficult to describe visual attribution maps, either by neglecting less discriminative features or by non-experts. Accordingly, as GAN-based visual explanation-related methods were presented, counterfactual reasoning was proposed that could not only generate a more realistic attribution map, but also explain the model system making in hypothetical situations. For example, as shown in the figure below, counterfactual reasoning is a method that provides a visual map that explains where and how the brain with Alzheimer's disease needs to be changed in order to be classified as mild cognitive impairment. So we interpret the trained diagnostic model based on this counterfactual reasoning method and use the generated counterfactual map as guidance for performance improvement. Finally, we propose a way to improve both visual explanation and performance by repeating these two processes. As you can see from the figure, first we train a diagnostic model to interpret. The model used here is the CNN-based classifier, VoxCNN and SonoNet, which have shown a good performance in a medical domain, or the famously known ResNet are used. That is, it shows that it is a method applicable to various CNN models. After that, perform counterfactual map generation to interpret the decision of the trained diagnostic model. The feature extractor of the counterfactual map generator used the weight of the pre-trained diagnostic model as it is. In order to counterfactual map generation for multi-way situation, we concatenated the target condition in the form of the one-up vector to the counterfactual map generator. For example, if the input is an Alzheimer's disease brain and the target condition is a condition for a normal brain, the generated counterfactual map is a map that has an attribution to make the input into a normal brain. To this end, we used 5 loss functions. First, we use the cycle consistency loss for identity preservation of the input and the cross-entropy loss for whether it is classified as a target condition in a pre-trained diagnostic model. In addition, again, training strategy was used for realistic synthesized image generation, and elastic loss and total variation loss were adopted for sparsity and smooth synthesis of counterfactual map, respectively. We show the details of how the target condition is concatenated in the figure on the right. After tiling the target condition in the form of the one-up vector with the same shape as the corresponding feature maps, concatenation is performed channel-wise to enable more effective transfer. Furthermore, we use the counterfactual map not only as a visual explanation map to explain the model's decision, but also as a guidance for improving the model's performance. To this end, we showed a significant performance improvement compared to the baseline by designing an explanation-guided attention module that can effectively apply map guidance. This module is injected to all convolution blocks, and only this module is learned in the reinforced step. Finally, we propose a framework that improved both visual explanation and diagnostic performance by iteratively performing counterfactual map generation and reinforcement learning. Here's a dataset description. To help understand counterfactual reasoning, we used MNIST as a toy example, and structural MRI data were taken from ADNI and used after preprocessing. This dataset consists of classes of cognitive normal, mild cognitive impairment, and Alzheimer's disease. And we took data from ADNI 1 and 2, and this dataset trained the model with five-fold cross-validation. As you can see from the figure, it can be observed that the proposed counterfactual map generation performed well on the MNIST dataset. For example, the counterfactual map shows where the number 0 must be added and subtracted to change the number 1 or number 5 corresponding to the target condition. Here's a figure showing comparison of visual explanation with other attribution and GAN-based approaches using ADNI dataset. A map was generated to classify the Alzheimer's disease brain as a normal brain, and the ground truth map is a map calculated by subtracting the normal brain from the Alzheimer's disease brain. Unlike other comparison methods, the explanation map of our proposed method shows the intensity and localization most similar to the ground truth map, and the comparison of quantitative evaluation using normalized cross-correlation scores also achieved good performance. Finally, this is the page showing the experimental result for iterative explanation reinforcement learning. As shown in the figure on the left, as the iteration progresses, it can be confirmed that the map is gradually changed to a fine-grained map, and quantitative evaluation is also improved in all settings. Then more details on the code of our proposed method have been uploaded at this link. This is a README script on GitHub that explains the model training method according to the version and data description and mode of the library used. First, in order for this code to work, you must make sure to set the version to the requirement below. And the corresponding dataset can be confirmed and downloaded through the hyperlink below, and the training step corresponding to the mode number has been written down. For example, in mode 0, the loop training the diagnostic model is executed, and in mode 1, The loop training the counterfactual map generator for interpreting the previously trained diagnostic model is executed. If you just specify the mode in the second line and the strategy path in the third line, you can easily learn about the mode. And thank you for listening my presentation.